Hey guys, welcome back. So today we're going to finally start talking about multiplying vectors together. It's been an exciting voyage, but we're finally here and we kind of want to see, what does this even mean? Okay, so multiplying vectors, kind of not as straightforward as other things that we've covered. We've looked at a few different types of vector operations. For example, we looked at vector addition. Okay, now with vector addition, we had this idea that you could have two vectors. Let's say we had a vector here, and then we had another vector here. Okay, so let's say that this one is vector A, and then we had a vector B, and then what we would get is when we add them together, we would get some kind of resultant vector, right? That would go from the very beginning to the very end, the very tip there, right? So this kind of made sense. And this would be our vector r. So if we imagine vectors as displacements, you can imagine that as you walk from the beginning of A to the end of A, and then you walk again from there to the end of B, your total displacement will be this vector r. Okay, so vector addition makes a lot of intuitive sense, where you can just sort of line them up this way and chain them up as many vectors as you want, and then the resultant is from the very beginning to the very end. Vector addition. Good, intuitive, I like it. We also looked at the idea of subtracting vectors, right? Vector subtraction. Now, vector subtraction was a little interesting. The key idea behind vector subtraction was that if you have a vector A, then having another vector, the same magnitude as A, but the opposite direction, this is what we call negative A, right? So if you're trying to add A plus negative A, that's the same as saying A minus A. So A minus A would equal 0, right? So again, if it's a displacement, you start here, you walk to here, and then you walk back, your total displacement is 0. You're back to where you started from. So subtraction makes sense, as negative means opposite direction of a vector. Okay, good, great. Also very intuitive. Finally, we also looked at multiplying a vector by a scalar. Okay, so we looked at this. So for example, we might have wanted to have a vector A and then multiply it by 2. What does this mean? Well, what it means is we're doubling the length of the vector, right? So we're changing the magnitude. Right, so we could have this, and if we were to have two of them, we'd basically just be increasing the length here. And so this is what we have the idea here, multiplying by a scalar. And basically a scalar multiplication is going to scale the magnitude of the vector, right? That's what it does. A scalar will scale, stretch, or maybe compress the length of the vector, but not change its direction. So this also makes a lot of intuitive sense. But now we're moving on to the next part, the hard part, the interesting part, about what happens when we multiply two vectors together. What does this even mean, right? If we have just two sort of random vectors and we multiply them together, what do we get? How do we get anything? All right, so let's try and build a little bit of an intuition about what this might mean. What I want to do is I want to imagine, use our imagination, a few different scenarios about what this might mean. And I want to start with the simplest possible scenario that I can imagine, and that is where we have parallel vectors. Okay, so for me, if we have two parallel vectors facing in the same direction and try and multiply that together, that's probably the simplest scenario that I can imagine. So let's start out with a vector here. Let's call this vector A, and then we'll also have another vector parallel to vector A, and we'll call this vector B. I know, it's surprising. So let's define these vectors here. I'm going to say that A is equal to 3i hat, okay, and vector B is equal to 2i hat. Okay, so we've got this this idea. You have A and B, and what would we get if we try and multiply them together? Can we get anything? Can we get a vector C? Well, you know, maybe we can. As I look at this, it reminds me a lot of scalar multiplication, right? Where they're pointing in the same direction, so the final vector should probably be in that same direction, and the magnitude of that vector would be the magnitude of A times the magnitude of B. I mean, this just sort of makes intuitive sense to me, where C would be equal to 6i hat. I think that kind of makes sense, right? We would get some product vector here that is C. And it's just, yeah, the magnitudes multiplied together and you preserve the same direction. Great. Okay, building something here. Let me take this scenario and let me tweak it a little bit, make it a little bit less simple. What I want to do is now consider if we have antiparallel vectors. Okay. What does this mean? Well, it means we have the same vectors as before, but now they're facing in opposite directions, right? That's what antiparallel means. So let's imagine that vector B is now facing in this direction. Okay, so we've got vector A, which is equal to 3i hat, and vector B, which is equal to negative 2i hat. Okay, now A times B, what is it? Well, it kind of looks like it should be negative 6i hat, right? Maybe negative 6i hat. But why would that be? You know, why would this be? You know, we had an idea before where your direction is preserved and your magnitude is multiplied together. But why now does the direction become to the left? Because that sort of seems to me like, well, B is to the left and A is to the right. Multiplying together, you get a vector to the left. Why is B more important than A? I don't see any good reason why B is more important than A. Could just as well be to the right, right? Like if I turned my head around, maybe I could make this resultant different. If I change my positive and negative axes, would the result of this product be different? It seems arbitrary. This direction seems arbitrary. I don't like it. I don't like this direction. The magnitude I can get behind. I think 6 or negative 6, this size makes sense, but this direction I don't like. I don't see why it would be left over right or right over left or whatever. So already things are getting a little bit complicated with the direction. Now let me tweak this again and make it the general case. Okay, so now we have the general case of two arbitrary general vectors, right? So in this case, we might have something like, let's say we have a vector A that's pointing like this, and a vector B that is pointing like this. And well, let's make it a little bit bigger. Something like that. Okay, so let's call this now vector B. And this one over here is going to be vector A. Okay, so we've got two general vectors. How can we possibly multiply these two together in a way that makes sense, that sort of builds on what we were developing with the parallel or anti-parallel scenarios? Well, okay. What if we were to connect these two vectors together so they start at the same location, right? So let's move vector B over to here. So now they're starting sort of at the same location. Well, you can imagine they're sort of like forces acting on something, and they're acting in slightly different directions, but they are sort of overlapping a little bit. So we could maybe get some kind of multiplication here where they're acting in the same direction, or how much they're acting in the same direction. So what I'm thinking is you could essentially take a projection of one vector onto another like this, forming a 90-degree angle here, and you could create sort of a component here of B, a component of B on A, right? So sort of like that. And now maybe you could get a magnitude. You could multiply A times the component of B that is parallel to A, and you could get a magnitude out of this. I think that kind of makes sense. But as far as direction goes, I see no way to choose a direction. I have no idea. I mean, even with antiparallel, I didn't know if it was left or right. Those seem to be the only two choices. But in this case, the choices are what? Along A? Why not along B? Why not somewhere in between? Or I don't know. So it seems impossible for me to choose a direction. This kind of thinking is what's going to develop into our first real concept of vector multiplication. That's what we're going to see right now. All right, so what we're looking at now is creating this idea of a dot product. Okay, if you're using the Young's textbook, they call it a scalar product. But the most common name for this that you'll find in most places in English is a dot product. So the idea is basically what we were just talking about. If we have two arbitrary vectors, let's say here is A, and then we have another one that, another vector here that we'll call B. So let's just draw vector B just like that. Then we can actually find a way to multiply them together. I mean, it's not going to be exactly the same as a scalar multiplication, but it's going to be kind of analogous, right? So if we have B here and A, we're going to be able to define a concept where we can take A dotted with B, and we're going to get an answer. We're going to do basically what I suggested. We're going to project B onto A, creating a component of B that's parallel to A, and we'll multiply those together. So we're going to say this is equal to the magnitude of A times the magnitude of this component of B that is parallel to A. And what I want to note is that this is going to give us a scalar, okay? There is no direction that is preserved here, okay? We've basically given up on trying to define a direction from this product, but we will get a magnitude out of it, and that magnitude is useful, okay? So, can we figure out what B sub A actually is? And we can, okay? So B sub A in this case, we can actually calculate it if we define this angle. If we define the angle between vectors B and A as phi, then using trigonometry, we can see that B sub A is the adjacent angle to phi. So we know that cosine of phi is equal to adjacent over hypotenuse, right? Vector B is the hypotenuse because this is the right triangle right there. And so we can solve for B sub A, and that's going to be equal to B cosine of phi, okay? We're using phi here as the separation between these two vectors. So we can now define this dot product as A dotted with B is equal to AB cosine of phi. And we've done it. We've defined a scalar product because the result is a scalar, right? No direction, typically called a dot product because you use the dot symbol to represent this kind of multiplication. Great. Okay, this is good, but you're thinking, that seems kind of arbitrary the way I chose A to be this dominant vector and I took the projection of B onto A. Like, why is A more special than B? What if b is the dominant vector? What if we did it that way? Okay, well, let's take a look. Let's do the same thing, but we'll treat b as the dominant vector. Okay, so in this case, what I want to do is I want to take a projection of A onto B, where this winds up being a right triangle. What we see here is we create this length here, and this length is going to be A sub B, the component of A that is parallel with B, and we still have the same angle phi here. Well, in this case, we can see that, let's say we're still using the same angle phi. In this case, we now have A sub B as the adjacent side to this angle, and vector A is the hypotenuse. So in this case, cosine of phi is equal to adjacent over hypotenuse. And so if we were to define A dotted with B as equal to A sub B times the magnitude of B, then we can substitute this in. We can see that A sub B is equal to A cosine of phi, and thus A dot B is equal to A B cosine of phi. And as we can see, it's exactly the same equation. So we're not actually saying which of these vectors is the dominant or most important one. We're actually treating them equally. The math is symmetric. It works out both ways. What we're essentially doing is we're creating some kind of a measure of alignment between these two vectors, or a measure of parallelness, right? How close to parallel are they? Or maybe you could call it a measure of togetherness, right? All of these ideas, they work because, let's take a look at this. What happens when phi is equal to 0 degrees? Okay, so if this angle phi is 0 degrees, then they are parallel with each other. And so when they are parallel, we know that the cosine of phi is going to be equal to 1, right? Let's remember what the cosine graph looks like. Okay, cosine graph looks something like this, right? This is the cosine graph, where this is 180 degrees, and this here is going to be 90 degrees, right? And here we have 0 degrees. So 0 degrees, we have the maximum value for cosine. It's going to be 1. And so in this case, A dot B is simply equal to the magnitude of A times the magnitude of B times cosine phi, which is 1. So it's just going to be AB. And this is maximum alignment, maximum togetherness. That's where we get the maximum value for the dot product. But as we increase this angle phi away from 0 towards 90 degrees, what happens? Well, at 90 degrees, we know that the cosine of phi is equal to, here, it's equal to 0. Okay, it's equal to 0. So that means A dot B is going to be equal to AB times 0, which is 0. Okay, so when we have a perpendicular arrangement, there is the minimum parallelness, minimum togetherness. They're pushing not together at all, okay? Minimum alignment, and so the value of our dot product is going to be 0, right? It's telling us that these two vectors are at 90 degrees from each other. And finally, what happens when phi becomes larger than 90 degrees? As it moves past that, what do we get? Well, as we move past 90 degrees, let's say between 90 and 180, we see that the values become negative. Okay, so in this case, cosine of phi is going to be less than 0, and A dot B is going to be negative. Right? You can imagine when phi is at 180 degrees, and that means they're facing opposite directions, while 180 degrees here is equal to -1, right? So if phi is equal to 180 degrees, cosine of phi equals -1, and thus A dot B is going to equal negative AB, right? So that's the maximum negative amount you can have. So when the value for the dot product is negative, that's essentially telling us that these two vectors are essentially facing opposite directions, right? When it's 0, they're orthogonal. When it's positive, they're essentially facing the same direction. And as they get to 0, you get the maximum value, and when you get to 180, you get the maximum negative value. It's going to be symmetric because the cosine function here is symmetric. So this is the dot product, sometimes called the scalar product. Next, we want to look at how to calculate this in another way. Okay, we're going to look at another way to compute the dot product using component vectors. Okay, we spent a lot of time learning this kind of IJK unit vector notation. So let's use it. Let's see if we can use that to describe dot product, and we can. So let me bring back our lovely little picture here. Now we had kind of assumed that vector A was parallel with the x-axis, horizontal here, but in general we want to be able to look at any two general vectors, so we can't really just assume that's going to be true, right? Okay, so let's put that there, and now we'll define our x and y axes just like that. And, you know, technically speaking, there could be a z-axis here, right? I mean, why not? So we could have three-dimensional vectors sort of like that. No reason why it couldn't be. So let's label these. We've got our x-axis, our y-axis, and our z-axis. Now, okay, I want to write down the general form for vector A and vector B in 3 dimensions. And that's going to look something like this. Vector A, we can write down using IJK notation as A sub x I hat plus A sub y j hat plus A sub z k hat. Remember that? Okay, we learned about this unit vector notation. Vector B is the same way. B sub x I hat plus B sub y j hat plus B sub z k hat. Okay, so we've got this kind of unit vector, component vector notation. Now what I want to do is I want to write down a formula for A dot B. Okay, how can we do that? Well, what I can basically do is I can say this is going to be equal to, if this is A, and if this is B, then I should be able to write down A dot B as A dot B, right? And now I've got, instead of 2 vectors, I have 6 vectors. I have AX I hat, AY j hat, AZ k hat, BX I hat. I have got 6 different vectors. Some of them are added, some of them are being dotted together. So what I have to do now is distribute through all of these different terms. So I'm going to wind up with AX I hat dotted with BX I hat plus AX I hat dotted with BYJ hat plus AX I hat dotted with BZK hat. I'm going to wind up and then do the same with AYJ hat and AZK hat and distribute everything through. I'm going to wind up with 9 different product terms here. So it's a little bit detailed. Let me go through and get all of this written out for you right here. Okay, so I've gone ahead and I've written all of these different terms out, and we've got 9 different terms, right? So we had AX I hat dotted BX I hat. We see that here. AX plus AX I hat dotted with BYJ hat. We see that here. So I've got all the terms distributed through, written down, all 9 of them, and we can see we've made a huge big mess, okay? It is a lot of terms going all over the place. Why did we do this? How does this help us? big mess, but there is a key here that helps us simplify it. What is ax I hat dotted with bx I hat going to be? More specifically, what I'm asking is, what is I hat dotted with I hat going to be? Because that carries all of the direction information, right? Well, let's think about this. If we remember our, we're doing purple here. If you remember our A dot B formula, we said that this was equal to A, magnitude of A times the magnitude of B times the cosine of the angle between them, right? So in this case, what do we get? Well, the magnitude of I is 1. The magnitude of I is 1. And the cosine, well, what's the angle between them? Well, they're parallel, so the angle between them is 0 degrees. And we know that equals 1. Cosine of 0 is 1, so I dot I is equal to 1, isn't it? Makes sense. These are unit vectors with magnitude 1, and they're parallel to each other, so you dot them together, you're just going to get the number 1, the magnitude 1. And that's going to be the same with any unit vectors. So I dot I is equal to 1, but so is j dot j. In fact, let me do this in a different color. I dot I and j dot j, and also k dot k, these are all equal to 1 because they're all parallel to each other. By the same token, what is I dot j going to equal? Well, in this case, I and j are perpendicular, so the angle between them is 90 degrees. Cosine of 90 is 0, and so I dot j is 0. I dot j is 0. What about I dot k? What about k dot j? They're all going to be 0, right? All of these orthogonal unit vectors are going to be 0. I dot k is 0, and j dot k is 0. So this is what's going to help us simplify these 9 messy terms that we've expanded out after distributing everything. We're going to see that this term survives. I dot I is going to be 1. J dot j is 1. K dot k is 1. Everything else involves unit vectors that are at 90 degrees with each other, and so these dot products all go to 0 and they disappear, just like that. So what we're left with is actually a relatively simple formula for calculating A dot B, and that is equal to AX BX plus AY BY plus AZ BZ, and that's it. We've done it. We figured out a way to compute a dot product using only their component vectors, and it actually turns out to be a pretty simple computation. Now, what I want to do is I want to sort of give you a graphic representation of what we're doing here. And what I want to do is I want to consider this A and B vector as we drew them down over here. Okay, the idea is we're going to have component vectors here for B. So this is going to be B sub y, right? And we also have a kind of a B sub x over here. Likewise, we can also have A sub x component vector and an A sub y component vector that might look something like that, right? So this is going to allow us to look at a graphical version of the dot product and what we're doing here, right? So we're trying to compute A dot B. And in this case, we're only going to look in 2 dimensions. So instead of having 9 different terms, we're only going to have 4, right? What we're going to have is we're going to have A dot B is going to equal AX I hat dotted with BX I hat plus AX I hat dotted with BY J hat plus AY J hat dotted with BX I hat plus AY J hat dotted with BY j hat. So we're going to have 4 different terms here, okay? And we're just going to graphically show you using these component vectors what this looks like. So let's start out with this first one. So we have ax I hat. So that's going to look something like this, right? And then bx I hat. So bx I hat is smaller, right? Something like that. And then next here we have byj hat. Yeah, that's right. Something like that, right? And dotted with ax I hat. So we had that already. It was this longer arrow. Next we have ayj hat. So that's going to be a smaller y component. And bx I hat, which is this smaller bx component. And then here we have byj hat and dotted with ayj hat, which is going to be a smaller vertical one, just like that. Okay, so the idea is these are the graphical representations of what we're doing when we take this dot product with these 2 vectors a and b that we're treating them as simply in the x and y plane. Okay, so what do we get here? Well, graphically, we can see that these 2 terms are orthogonal to each other. So this angle is 90 degrees. We know that cosine of 90 is going to be 0. And so we know that this becomes 0 and this becomes 0. So we're adding zeros here. Meanwhile, for these, we can see that they're parallel. And so we're going to get the cosine of 0, which is 1. And so this is just going to give us ax bx plus 0 plus ay by. And so you see we've rederived graphically sort of the 2-dimensional version of the equation we had here, just because it's easier for me to draw 2-dimensional vectors. So graphically it checks out, right? Graphically works. Okay, this is really good news for us. And so what we're left with is 2 different ways to compute a dot b. We can compute it as either the magnitude of a times the magnitude of b times the cosine of the angle between them, or we can compute it as ax bx plus ay by plus az bz. And in the 2-dimensional case, there is no az or bz, so that's just 0, and you're reduced to ax bx plus by ay bi, which is what we got here, right? But in the general 3-dimensional case, this is going to be the formula. So there we go. We've successfully created this multiplication operation called the dot product, and it gives us a scalar. So sometimes it's called a scalar product. There's no direction after we do this dot product, but there is a magnitude. And the magnitude essentially represents sort of how maximally aligned the 2 vectors are. When they are perfectly aligned, you get this maximum value. When they're orthogonal, you get 0. And when they're antiparallel, you get a negative sign. You get anything past 90 degrees, you'll get a negative sign, which means they're sort of facing away from each other, but then you'll have the maximum negative when they're antiparallel. Hopefully this gives you some intuition about how the dot product works and 2 different ways to calculate it, using unit vectors and also using the angle of separation there. If you have any questions, please let me know in the comments below. And I have some exercises you'll be able to get on my website. Check the link in the description there to the website. You'll be able to find some PDF exercises that you can do for this. And in our next lesson, we're going to learn how to do another kind of vector multiplication, another kind of vector product that's a little bit different from this one. So I hope to see you there. And thanks. I'll see you then. Okay, bye-bye.